Close your eyes. Let your breathing slow, just a little. You are lying, right now, in one small corner of something almost impossibly vast. 8 planets, over 200 moons, a sun over 1,000,000 Earths wide, and a storm on a distant planet that's been spinning for longer than anyone has been alive. Tonight, we're going to visit all of them, slowly, one by one, starting with the star that holds everything together, and ending somewhere far past Pluto, at the edge of where the sun's influence finally fades into the dark. You don't need to hold on to any of it. Just let your shoulders settle and let the journey begin. There's no rush anywhere in tonight's story. Every world we visit moved into place over millions, sometimes billions of years, and nothing about how you listen tonight needs to happen any faster than that. Drift in and out as much as you need to. The planets will still be there, exactly where we left them, whenever your attention returns. Before we visit any particular world, it helps to understand, gently, where all of them came from in the first place, because none of the planets we're about to see were built separately, on their own, in isolation. Every single one of them, from the smallest asteroid to the largest gas giant, came from the very same place, the very same cloud, the very same quiet beginning. Roughly 4.5 billion years ago, in an unremarkable stretch of the Milky Way, a vast cloud of gas and dust drifted slowly through the dark. Mostly hydrogen and helium, the oldest ingredients in the universe, but also, scattered through it, small traces of heavier material, carbon, oxygen, iron, silicon, left behind by generations of earlier stars that had lived and died long before this particular cloud ever existed. Something disturbed that cloud's quiet balance, perhaps the shockwave of a nearby supernova, rippling outward through the gas. And once disturbed, the cloud began, very slowly, to collapse inward under its own weight, gravity doing the same patient work it always does, pulling matter closer and closer together. As it collapsed, it began to spin faster, the way a skater spinning slowly draws their arms in and speeds up. And as it spun, it flattened, the way dough spreads and flattens when tossed and spun through the air, into a wide swirling disk, with the greatest concentration of material gathering at the very center. At that center, pressure and heat climbed higher and higher, until finally, hydrogen began fusing into helium. A star had switched on, our sun. Around that newborn star, the leftover material in the flattened disk, dust, ice, small rocky fragments, began doing what matter tends to do, given enough time and enough gravity. Colliding, sticking together, small grains became pebbles, pebbles became boulders. Boulders over millions of years became larger bodies still, sweeping up material as they orbited, growing steadily larger through countless slow collisions. Closer to the young sun, where temperatures were too high for ice to survive, only rock and metal could condense, giving rise to the 4 smaller, denser worlds we're going to visit first tonight: Mercury, Venus, Earth, and Mars. Further out, beyond a boundary scientists call the frost line, ice could survive alongside rock and metal, allowing much larger bodies to form, the 4 giant worlds waiting for us later tonight: Jupiter, Saturn, Uranus, and Neptune, and scattered through everything in between, and everything beyond, the leftover pieces that never quite became a planet at all. Asteroids, comets, dwarf planets drifting in the deep cold at the very edge of everything. We'll visit those too, in their turn, quiet reminders of exactly how this whole system came together in the first place. It's worth sitting with that thought for a moment as we begin, gently, without needing to hold it too tightly. Every world we visit tonight, however different they may look from one another, however strange or familiar, came from the very same cloud, the very same collapse, the very same patient process of small things gathering slowly into something larger. Neighbors, in the truest sense, all of them built from the same original material, simply arranged differently depending on how close or how far they happen to end up from that one bright star at the center. This process, scientists sometimes call planetary accretion, wasn't smooth or gentle in its earliest stages. The young solar system was a genuinely violent place, filled with countless smaller bodies, constantly colliding, merging, and occasionally shattering each other entirely. A long, chaotic period of building up and breaking down that likely lasted many tens of millions of years before anything resembling the calm, orderly system we know today finally settled into place. Some of those early collisions were catastrophic almost beyond imagining. Entire small worlds colliding head-on, their debris scattering outward to eventually become part of some other larger body forming nearby. It's a genuinely turbulent origin story for what has since become such a remarkably stable, orderly arrangement of orbits, one that has held largely steady for over 4 billion years since. Even today, faint echoes of that early chaos remain scattered throughout the solar system. Tilted planets, backward spinning worlds, oddly shaped moons, each one a small, quiet record of some ancient collision or near miss, still carried, visibly billions of years later, by the worlds we're about to spend tonight exploring. There's one more piece of this early story worth knowing, gently, before we begin, because it helps explain a few of the stranger details we'll encounter later tonight. The planets we're about to visit didn't necessarily form in exactly the positions they occupy today. Many scientists now believe the giant outer planets, Jupiter, Saturn, Uranus, and Neptune, actually migrated significantly after their initial formation, drifting slowly inward and outward over the solar system's first few 100 million years, gravitationally tugging on one another in a long, slow, complicated dance before finally settling into something close to their present stable orbits. One version of this idea, sometimes called the Nice model, named after the French city where the theory was developed, rather than any particular quality of the model itself, suggests that Jupiter and Saturn once orbited much closer together than they do now, and that their shifting gravity, as they slowly drifted apart, scattered enormous amounts of icy debris throughout the solar system, an event some scientists connect to a mysterious period roughly 4 billion years ago called the Late Heavy Bombardment, when the inner planets, including the young Earth and Moon, appear to have been struck by an unusually high number of large impacts within a relatively short window of time. Evidence for this bombardment is still visible today, quite literally, in the heavily cratered face of our own moon, a patient record of that ancient, turbulent rearrangement, still plainly readable billions of years later. It's a genuinely humbling thought to carry gently into the rest of tonight's journey, that the calm, orderly arrangement of planets we're about to explore, one by one, wasn't simply how things always were. It was earned, in a sense, through hundreds of millions of years of slow, gravitational jostling, collisions, and rearrangement, before finally settling into the quiet, stable pattern that has held steady ever since. The same pattern still holding, patiently, right now, above whatever roof happens to be over your head tonight. Everything from here on will simply be a matter of distance. Closer worlds shaped one way by that central fire, further worlds shaped another, all of it flowing outward from the same single point of light we're about to spend some time with. It's worth noticing, gently, how much of tonight's journey depends on that same simple idea, distance from the center changing everything. The same cloud, the same collapse, the same basic ingredients, and yet, depending on nothing more than how close or how far a particular clump of material happened to settle, entirely different kinds of worlds emerged. Small and rocky close in, massive and gaseous further out, icy and quiet further still. No plan, no design, simply physics and distance, working themselves out patiently over millions of years, the same way they still do today. At the heart of everything we're about to see sits a single star, ordinary in almost every respect when compared to the wider galaxy, and yet, from where you're lying right now, it is the single most important object in existence. Every bit of warmth you have ever felt on your skin, every plant that has ever grown, every day and night your entire life has been shaped around, all of it traces back to this one star. The sun holds more than 99% of all the mass in the entire solar system. Every planet, every moon, every asteroid, every comet, all of it combined makes up less than 1% of everything orbiting out there. Jupiter alone accounts for more than 2/3 of that remaining fraction, meaning the Sun and Jupiter together hold the overwhelming majority of all the mass in the entire solar system. With every other world we'll visit tonight, including the one you're resting on right now, making up little more than a rounding error by comparison. If you tried to picture the Sun's size next to Earth, the comparison barely makes sense using ordinary language. Over 1 million Earths could fit inside it, with room left to spare. At its core, temperatures reach somewhere around 15 million degrees, hot enough and dense enough for hydrogen nuclei to fuse together into helium, the same basic process we touched on earlier tonight, releasing an almost incomprehensible amount of energy in the process. Every single second, the Sun converts around 600 million tons of hydrogen into helium. Every second. And it's been doing this steadily, reliably, for around 4.5 billion years already, with enough fuel remaining to continue for roughly 5 billion years more. That energy doesn't reach the surface quickly either, which is one of the stranger facts about our own star. A single photon of light, created deep in the Sun's core, can take anywhere from 10,000 to 170,000 years just to fight its way outward to the surface, bouncing and scattering constantly through the dense material along the way. Once it finally does escape, though, that same photon crosses the 93 million miles to Earth in just over 8 minutes. So the warmth touching your skin on any ordinary afternoon may have begun its journey inside the Sun's core longer ago than human civilization has existed, only to cover the final stretch to your window in the time it takes to make a cup of tea. The Sun's surface, the part we can actually see, isn't solid at all. There's no ground to stand on anywhere on the Sun. It's a churning, boiling layer of plasma, glowing at around 5,500 degrees, marked by dark, cooler patches called sunspots, regions where the Sun's powerful magnetic field suppresses the usual flow of heat from below. Some sunspots grow large enough to swallow Earth several times over. These sunspots rise and fall in number over an 11-year cycle, a slow, steady rhythm the Sun has followed for as long as careful records have been kept. Periods of high activity followed by quieter stretches, followed by high activity again. A patient heartbeat running through the Sun's otherwise steady, reliable burn. Above that visible surface sits the Sun's atmosphere, thin and strangely far hotter than the surface itself. The corona, the outermost layer, reaches temperatures of over 1 million degrees, hundreds of times hotter than the surface directly beneath it. A genuine mystery scientists are still working to fully explain, something to do with the tangled, snapping magnetic fields that constantly twist and release energy above the Sun's surface. Every so often, that magnetic tension releases suddenly and violently, in the form of a solar flare, an enormous burst of energy and radiation flung outward into space. Sometimes, alongside a flare, the Sun releases a coronal mass ejection, a vast cloud of charged particles hurled outward at incredible speed. When one of these clouds happens to be aimed toward Earth, it can trigger the beautiful glowing auroras near our planet's poles, the northern and southern lights, a genuinely stunning reminder that our quiet blue planet is connected, invisibly, to the restless star 93 million miles away. The Sun is roughly halfway through its life. In around 5 billion years, it will begin to swell into a red giant, and eventually settle into a small, quiet white dwarf, a story we've touched on before and won't dwell on again tonight. For now, it's enough simply to picture it as it is right now, calm and steady, holding this entire system together the way it has for billions of years, and will continue to, for billions more. Every scrap of light in the images we've gathered tonight, every glowing nebula, every distant planet's reflected glow, ultimately traces back to fusion happening somewhere, in some star. The same quiet process burning steadily at the center of everything we're about to explore. Everything else we visit tonight orbits this one star. Let's move outward now, gently, to the first small world closest to its light. It's worth noting, before we move on, that despite how central and enormous the sun feels to everything in this story, it is, by the standards of the wider galaxy we spent another evening with, a remarkably average star, neither the largest nor the smallest, neither the hottest nor the coolest, simply one ordinary, reliable star among the hundreds of billions scattered across the Milky Way. Ordinary, and yet, from where you're resting right now, still the single most important object that exists. There's a quiet kind of trust involved in simply accepting the sun's steadiness, the way we all do, every single day, without ever really thinking about it. Somewhere above the clouds right now, that same enormous patient fire is burning exactly as it was yesterday, exactly as it will tomorrow, exactly as it has for longer than anything living has existed to notice. You don't have to think about it to benefit from it. You never have. It simply continues, whether anyone is paying attention or not, the quiet, reliable engine underneath every single day you've ever lived. The closest planet to the sun is also in many ways one of the strangest worlds in the entire solar system, a small, gray, heavily cratered planet that experiences some of the most extreme conditions anywhere we'll visit tonight. Mercury is tiny, barely larger than our own moon, and it orbits the sun faster than any other planet, completing a full lap in just 88 days. If you lived on Mercury, a year would pass in less than 3 months. But here's where it gets strange. Despite being the closest planet to the sun, Mercury rotates on its axis incredibly slowly, so slowly that a single day on Mercury, meaning one full rotation relative to the sun, actually takes about 176 Earth days to complete, longer than Mercury's entire year. It's a genuinely odd relationship between its spin and its orbit, one that took astronomers a surprisingly long time to work out correctly. Because Mercury has almost no atmosphere to speak of, nothing to trap or distribute heat, its surface experiences the most extreme temperature swings of any planet in the solar system. During the day, temperatures can soar past 400 degrees Celsius, hot enough to melt certain metals. At night, with no atmosphere to hold on to any of that warmth, temperatures plummet to nearly negative 180 degrees. The difference between Mercury's day and night on the very same small world is more extreme than almost anywhere else we know of. And yet, strangely, in permanently shadowed craters near Mercury's poles, regions where sunlight never quite reaches, scientists have found evidence of water ice, tucked away in the coldest, darkest corners of the hottest planet in the solar system. It's a strange, quiet detail worth sitting with for a moment. Ice, patiently surviving in the shadow of the world closest to the sun. Mercury's surface itself is heavily cratered, more so than almost anywhere else we'll visit. A landscape that has been battered by impacts for billions of years, with very little to erase or soften the scars. Without meaningful weather, without plate tectonics reshaping the surface, without much of anything to disturb it, Mercury simply carries the record of nearly every major impact in its long history, written plainly across its gray, ancient surface. One particularly large feature, the Caloris Basin, is one of the biggest impact craters in the entire solar system, stretching over 1,000 miles across, the scar of a truly enormous collision sometime in Mercury's distant past. The force of that impact was so great that it sent shockwaves through the entire planet. And on the exact opposite side of Mercury from the crater itself, scientists have found strange, jumbled, chaotic terrain, sometimes called weird terrain, thought to have been created by those same shockwaves converging violently on the far side of the planet. Despite its small size and lack of atmosphere, Mercury does have a surprisingly large iron core, relative to its overall size, taking up around 85% of the planet's radius, far more, proportionally, than Earth's own core. Scientists believe an ancient, powerful collision may have stripped away much of Mercury's outer rocky layers early in its history, leaving behind an unusually dense, metal-rich world. It's a small planet, easy to overlook next to its larger, more dramatic neighbors. But Mercury holds its own quiet extremes: the fastest orbit, the widest temperature swings, ice hidden in permanent shadow beside some of the most scorched ground anywhere nearby. A strange little world, closest of all to the light, and yet, in its own way, one of the coldest and darkest too. Only two spacecraft have ever visited Mercury closely: Mariner 10 in the 1970s, and Messenger, which orbited the planet for 4 careful years starting in 2011, slowly building the detailed map of this small, strange world that scientists still study today. Let's drift outward now to the second planet from the Sun, a world that looks on the surface of things deceptively similar to our own. Mercury has been watched by human eyes for thousands of years, appearing briefly near dawn or dusk before slipping back into the Sun's glare. One of the 5 planets visible without any telescope at all, known to nearly every ancient civilization that ever tracked the sky carefully, long before anyone understood what it truly was. It's strange to think that Mercury, for all its extremes, was once considered by some ancient cultures to actually be 2 separate objects, a morning star and an evening star, since it's only ever visible near sunrise or sunset, tucked so close to the Sun that it never strays far from its glow in our sky. It took careful, patient observation over generations to realize both sightings were the very same small, fast-moving world, quietly completing its tight, quick orbit around the star it never strays far from. Venus is often called Earth's twin, and at a glance, it's easy to understand why. Similar in size, similar in mass, formed from much the same raw material, in roughly the same era, but with a thick, crushing atmosphere and a surface hot enough to melt lead. It's a world of extremes all its own, in a neighboring stretch of that same young solar system we described earlier tonight. If you were simply comparing statistics on a page, Venus and Earth would look like siblings. But step past those numbers, and Venus reveals itself to be one of the most hostile places in the entire solar system. A world that took a very different path from our own, despite such a similar beginning. Venus is wrapped in a thick, crushing atmosphere, made up almost entirely of carbon dioxide, dense enough that the pressure at its surface is more than 90 times greater than what you're feeling right now, lying wherever you are on Earth. It's roughly equivalent to the pressure you'd experience nearly a kilometer beneath the ocean's surface. Any spacecraft attempting to land on Venus has to be built almost like a submarine designed for the deepest parts of our own oceans, simply to survive the crushing weight of the air itself. That thick atmosphere traps heat with extraordinary efficiency, a runaway greenhouse effect unlike anywhere else nearby. Surface temperatures on Venus reach around 460 degrees Celsius, hot enough to melt lead, and remarkably hotter even than Mercury, despite Venus sitting much further from the Sun. Mercury may be closer to our star, but Venus's thick blanket of atmosphere traps far more heat than Mercury's bare, airless surface ever could. High above that scorched surface, thick clouds of sulfuric acid drift constantly across the planet, reflecting sunlight so effectively that Venus is the brightest object in our night sky after the Moon, easily visible with the naked eye as a brilliant point of light in the evening or morning sky, something people have watched and wondered about since long before telescopes existed at all. Venus also rotates unlike any other planet in the solar system. It spins backward, in the opposite direction to nearly everything else out here, and does so incredibly slowly, so slowly that a single day on Venus, one full rotation, takes longer than an entire Venusian year. If you stood on Venus's surface and somehow survived to watch, the sun would rise in the west and set in the east, the reverse of what we're used to, and the whole cycle would take longer than the planet's full orbit around the Sun. Nobody knows for certain why Venus rotates this way. One leading idea points to an ancient, enormous collision sometime in the planet's distant past. A single massive impact, violent enough to flip the planet's spin entirely, similar in spirit to the kind of chaotic, formative collisions that shaped so much of the early solar system. Venus's surface itself, hidden beneath that thick veil of cloud, was mapped in detail using radar by spacecraft like Magellan in the early 1990s, revealing a landscape covered in volcanoes, more of them in fact than any other planet in the solar system, over 1,500 major volcanic features identified so far. Some scientists believe Venus may still be volcanically active today, its surface slowly resurface itself. Last, below, was some of the deepest volcanic veins of all, molten rock rising up from below, erasing and rewriting the landscape gradually over time. Because of this apparent resurfacing, Venus has surprisingly few visible impact craters compared to a world like Mercury or our own Moon, its restless geology quietly erasing the scars of ancient collisions far faster than most other rocky worlds nearby manage to. As we picture Venus tonight, a world so similar to our own in size and origin, and yet, through some combination of a runaway greenhouse effect and an ancient violent history, transformed into one of the most hostile places imaginable. A quiet reminder of just how narrow and how fortunate Earth's own particular balance really turned out to be. We'll drift past Venus now and toward that fortunate balance itself, the world you're resting on right now. It's worth remembering that Venus, for all its hostility today, is often the very first planet most people ever point out to a child in the night sky, mistaken, more often than not, for an unusually bright star. A blazing, beautiful light, entirely deceptive about the crushing, scorching world hiding beneath its clouds. There's something worth sitting with in how differently two such similar starting points can unfold. Earth and Venus, born from nearly identical material, at nearly the same time, only a modest distance apart by cosmic standards. And yet somewhere in their earliest few 100 million years, small differences, a little more sunlight here, a little less volcanic outgassing there, compounded slowly into two entirely different destinies. One a world of oceans and quiet green growth, the other a scorched, crushing, golden-shrouded furnace. Small beginnings, given enough time, tend to become very large differences indeed. We won't spend too long here tonight, since this particular world, the one you're lying on right now, deserves its own evening entirely, its own long and careful telling another time. But no tour through the solar system would feel complete without pausing, briefly and gently, at home. Earth sits third from the Sun in what scientists sometimes call the habitable zone, that narrow, fortunate band of distance where temperatures allow liquid water to exist stably on a planet's surface. Not so close that oceans boil away, the way Venus's likely did in its distant past. Not so far that everything freezes solid, simply, quietly, exactly right. About 70% of Earth's surface is covered in liquid water, a detail so ordinary to us that it's easy to forget how genuinely rare it appears to be across the wider universe. As far as we've been able to determine so far, despite searching carefully, Earth remains the only place we know of, anywhere, where liquid water exists openly on the surface, and where life, as far as we can tell, has ever taken hold. Earth's atmosphere, a thin, precious layer of nitrogen and oxygen, does more quiet work than it often gets credit for. It shields the surface from harmful radiation. It burns up countless small meteors before they ever reach the ground. It traps just enough heat to keep the planet comfortably warm, without tipping into the runaway greenhouse effect that overtook Venus so long ago. And crucially, it's breathable, filled with oxygen released, as we touched on earlier tonight, by billions of years of quiet photosynthesis, the patient work of countless generations of simple organisms, long before anything resembling an animal ever existed. Beneath that thin atmosphere, Earth's interior churns slowly and constantly, a molten outer core generating a protective magnetic field that wraps around the entire planet, deflecting much of the sun's harmful radiation and solar wind. A shield Mars, as we'll hear shortly, largely lost long ago. And circling this one fortunate world is a companion unlike any other moon in the solar system, at least in proportion to its planet. Our moon is unusually large relative to Earth, roughly a quarter of Earth's diameter, far larger, proportionally, than almost any other moon compared to the planet it orbits. We touched on the moon's violent origin earlier tonight too. A Mars-sized body colliding with the young Earth, throwing debris into orbit that slowly gathered itself into the moon we see today. Since then, our moon has settled into something remarkably steady and useful. Its gravity gently stabilizes Earth's axial tilt, keeping our seasons mild and predictable, rather than wild and chaotic, the way a tilt left unchecked over millions of years might otherwise drift. Its pull raises the tides in our oceans, a rhythm so constant that entire ecosystems and entire human cultures have shaped themselves around it. The moon is also, slowly, drifting away from us, moving outward at a rate of about 3.5 centimeters every year, roughly the speed your fingernails grow. It's a change far too slow to ever notice within a single lifetime, but billions of years from now, it will have quietly reshaped both worlds in ways we can only estimate from here. Long ago, in Earth's own early history, the moon sat far closer than it does now, filling much more of the sky, and days themselves were shorter too, lasting only a handful of hours rather than the familiar 24 we're used to. A slow, patient lengthening that continues even now, one imperceptible fraction of a second at a time. It's worth resting on this for just a moment, gently, without needing to feel anything sharp about it. Of every world we're visiting tonight, only this one, so far, has managed to hold onto oceans and skies and living things for billions of uninterrupted years. Not because it was destined to, simply because the balance, this time, happened to hold. We'll leave Earth resting quietly now, and continue outward toward its smaller, colder neighbor. Every single person who has ever lived, every war and every kindness, every quiet, ordinary evening like this one, has happened on this one small planet, circling this one star, in this one small corner of the galaxy. It's worth letting that settle gently for a moment before we continue on to somewhere far less familiar. It's a strange kind of privilege, worth resting on gently, to exist on the one world in this entire tour that got the balance right. Not through any effort of its own, simply through fortunate placement, fortunate timing, fortunate proportions of water and rock and atmosphere. Every breath you're taking right now, slow and easy, wherever you happen to be lying, is only possible because of that one narrow patient stretch of good fortune, stretching back billions of years before you ever arrived to benefit from it. Mars, the fourth planet from the Sun, has captured human imagination longer and more persistently than almost any other world out here. A small, rust-colored planet that has been watched, wondered about, and written into stories for as long as people have looked carefully at the night sky. Mars is considerably smaller than Earth, roughly half the diameter, and colder, with an average surface temperature of around -60 degrees Celsius. Made up mostly of carbon dioxide, is less than 1% as dense as Earth's, nowhere near enough to trap significant heat, or to shield the surface effectively from radiation, or to support liquid water openly on the surface today. But Mars wasn't always this way. Some of the most compelling evidence gathered by rovers and orbiters over the past several decades points toward a very different ancient Mars, a planet that once had a thicker atmosphere, flowing rivers, and quite possibly shallow seas, sometime in its first billion years of existence. Dried river channels, ancient lake beds, mineral deposits that here on Earth only form in the presence of water, all of it scattered across the Martian surface, quiet evidence of a warmer, wetter world that existed long, long ago. What changed, most likely, comes back to something we touched on earlier tonight as well. Mars is smaller than Earth, meaning its interior cooled more quickly, and as it cooled, its protective magnetic field weakened and eventually faded almost entirely. Without that shield, the solar wind, the constant stream of charged particles flowing outward from the sun, gradually stripped away much of Mars's atmosphere over the following billions of years, thinning it more and more until the thick, warm world that once may have been became the cold, dry, thin-aired planet we observe today. Mars is home to some genuinely extreme geography too. Olympus Mons, the largest known volcano in the entire solar system, rises nearly 22 kilometers high, roughly 2.5 times taller than Mount Everest, and spreads wide enough to cover an area close to the size of an entire country. It's long since gone dormant, but its sheer scale is a quiet reminder of just how different geology unfolds on a smaller planet, with weaker gravity and no plate tectonics to break volcanic activity up into smaller, more scattered peaks the way it does on Earth. Nearby, Valles Marineris, a vast canyon system, stretches for over 4,000 kilometers, deep enough and wide enough that it would swallow our own Grand Canyon many times over, easily one of the largest canyon systems anywhere in the solar system. Mars has two small, irregularly shaped moons, Phobos and Deimos, likely captured asteroids rather than moons formed alongside the planet itself. Small, lumpy, and quite unlike our own large, round moon. Phobos, the larger and closer of the two, orbits so near to Mars that it's slowly, gradually spiraling inward, and in tens of millions of years, it's expected to either crash into the planet's surface or break apart entirely under the strain of Mars's gravity, scattering into a faint ring around the planet. Because of its similarities to early Earth and its comparatively accessible distance from us, Mars remains the most actively explored planet in the solar system besides our own, home to rovers that have spent years patiently studying its rocks, its ancient riverbeds, and searching carefully for any sign, however small, that life may have once existed there too. So far, nothing definitive has been found, but the search continues, patiently, the same way it has for decades now, and will likely continue for decades more. Future missions are already being planned to bring samples of Martian rock and soil back to Earth for the first time. Careful, patient fragments of another world, gathered slowly over years of rover exploration, waiting for the day they might finally be studied directly in laboratories here at home. There's something quietly poignant about Mars, worth resting on gently before we move on. A world that may once have looked, in its own way, a little like early Earth, rivers, warmth, perhaps even the beginnings of something alive, only to slowly lose its atmosphere and its warmth and settle into the cold, quiet, rust-colored world we see today. A reminder again of how narrow and how fortunate Earth's own long stability has really been. Beyond Mars lies a wide, scattered region unlike anything we've visited so far. Not a planet at all, but the leftover pieces of everything that never quite became one. Mars has been visited by more spacecraft than any other planet besides Earth itself, a slow, patient accumulation of rovers and orbiters sent across the decades, each one adding a little more to our understanding of this small, cold, once wetter world, one careful mission at a time. Mars has captured more human attention and more human imagination than any other planet we'll visit tonight. Partly because it's the one world most people picture, however briefly, as somewhere we might one day actually stand. Whether or not that ever comes to pass, there's something quietly moving about a species barely a few 100,000 years old, looking outward at a cold, rust-colored world nearly 400 million kilometers away, and beginning, patiently, carefully, to wonder whether it might one day be reachable at all. Between Mars and the giant planet waiting for us next, there's a wide, scattered region called the asteroid belt, a vast ring of rocky and metallic debris left over from the solar system's earliest days, material that for one reason or another never quite managed to gather itself into a proper planet at all. It's easy, from popular imagination, science fiction especially, to picture the asteroid belt as a dense, chaotic field of tumbling rocks, spacecraft weaving frantically between them. The reality is far quieter, and far more spread out than that. The asteroid belt is genuinely vast, and the objects within it are on average separated by enormous distances, millions of kilometers apart in many cases. Spacecraft have crossed through the belt numerous times without any need for careful dodging at all, simply drifting quietly through mostly empty space. Scientists estimate there may be well over 1 million asteroids in the belt larger than a kilometer across, along with countless smaller fragments, pebbles, and dust. NASA's Dawn spacecraft became the first mission to orbit 2 separate destinations within the belt, visiting both Vesta and Ceres in turn during the 2010s, patiently gathering close-up images and data from 2 of the belt's largest and most distinctive residents. Despite that large number, the entire asteroid belt, if you combined every single object within it into one single mass, would still only add up to a small fraction of our own moon's mass, a genuinely modest amount of material spread across an enormous volume of space. The reason this region never formed into a planet comes back, largely, to its close neighbor. Jupiter, the giant world waiting for us just beyond, exerts such an enormous gravitational influence on this region that its pull constantly disturbs and scatters the material here, preventing these smaller bodies from ever settling calmly enough to gradually merge into something larger. Rather than gathering peacefully into a planet the way material did elsewhere in the young solar system, the asteroid belt's material was kept stirred up and separated, a kind of planet that never quite got the chance to happen. The largest object in the asteroid belt, Ceres, is substantial enough that it's classified today as a dwarf planet, roughly 940 kilometers across, and interestingly, believed to hold a genuine reservoir of water ice beneath its dusty surface, perhaps even a layer of briny liquid water further underground. We'll return to the topic of dwarf planets again later tonight, once we've traveled much further outward, to another, colder region entirely. Other notable asteroids include Vesta, one of the brightest objects in the belt, and occasionally visible from Earth, even without a telescope under the right conditions, and Pallas, another of the belt's largest residents. Each of these larger bodies carries its own particular history, its own particular composition, quiet fragments and survivors from the earliest, most chaotic period of the solar system's formation. Every so often, gravitational interactions, often involving Jupiter's powerful influence, nudge an asteroid out of its stable orbit within the belt, sending it drifting inward toward the inner solar system. Most of these wandering fragments simply continue harmlessly on new orbits. A small number, over the vast span of the solar system's history, have found their way to Earth. Some of our most valuable scientific samples of the early solar system's raw material have arrived this way, meteorites that fell from the sky, carrying with them small pieces of that original, ancient cloud we described at the very beginning of tonight's journey. The asteroid belt, in a quiet way, is less a place of danger, the way it's so often dramatized, and more a kind of vast, sparse museum, a scattered record of the raw material the whole solar system was built from, still drifting patiently in the space between the rocky worlds we've just visited and the giant worlds waiting for us next. Let's continue outward now, past this quiet, scattered boundary, toward the largest planet in the entire solar system. It's worth remembering, gently, that the asteroid belt sits at what feels, from Earth, like the halfway point of tonight's journey, though in terms of actual distance, it's really only the very beginning of the wider solar system's true scale. Everything from here outward, Jupiter, Saturn, Uranus, Neptune, and the icy realms beyond them, occupies a volume of space vastly larger than everything we've visited so far, a quiet reminder that the small, rocky worlds closest to the Sun, however familiar and important they feel to us, make up only a small, inner sliver of the solar system's true, enormous size. From here, the character of the solar system changes noticeably. Everything behind us has been small, rocky, and relatively close together. Everything ahead is enormous, gaseous, and separated by far greater distances, an entirely different kind of neighborhood, waiting quietly in the dark ahead. Every meteorite ever found on Earth carries with it a small, quiet piece of that same ancient scattered belt, material that has drifted, mostly undisturbed, since before the Earth itself had finished forming. Somewhere in a museum drawer or a private collection, a fragment of rock older than any mountain on this planet sits quietly, having traveled further and existed longer than anything else most people will ever hold in their own two hands. Beyond the asteroid belt, everything about the solar system changes in scale. We leave behind the smaller, rocky worlds we've spent the first half of tonight visiting, and enter the realm of giants, worlds so large that comparing them to Earth barely does justice to the difference. Jupiter is, by a wide margin, the largest planet in the solar system. Its mass is roughly 2.5 times greater than every other planet in the solar system combined. If you could somehow hollow Jupiter out, more than 1,300 Earths could fit inside it. It's a planet so large that it and the Sun actually orbit a shared center of gravity that sits just barely outside the Sun's own visible surface. A small but genuine reminder of just how much mass Jupiter really carries. Jupiter has no solid surface to speak of, at least none we could ever hope to stand on. It's a gas giant, made up almost entirely of hydrogen and helium, the same basic ingredients the Sun itself is built from. So much so that if Jupiter had been around 80 times more massive during its formation, it might have ignited its own nuclear fusion and become a small star in its own right, orbiting alongside our Sun as part of a binary system. It came surprisingly close in cosmic terms to being something entirely different. Even as it stands, Jupiter radiates more heat outward into space than it receives from the distant Sun, a leftover glow from its own formation, still slowly cooling, even after 4.5 billion years, a quiet echo of the same gravitational collapse that built every star we discussed on another night entirely. Jupiter's atmosphere is famous for its swirling, banded appearance, distinct stripes of orange, white, and brown, created by powerful jet streams racing through the upper atmosphere at speeds far greater than anything we experience here on Earth, some reaching well over 500 kilometers per hour. These bands and the storms that churn within them are driven partly by Jupiter's own rapid rotation. Despite its enormous size, Jupiter spins faster than any other planet in the solar system, completing a full rotation in under 10 hours, meaning a single day on Jupiter is less than half the length of a day here on Earth. The most famous feature on Jupiter's surface is the Great Red Spot, an enormous storm, wide enough to swallow Earth more than once over, that has been raging continuously for at least a few hundred years, quite possibly far longer than that. It's a genuinely strange thing to picture, a single storm, larger than our entire planet, outliving every human being who has ever watched it through a telescope, spinning quietly on, indifferent to the passage of empires and centuries below. Beneath that visible, swirling atmosphere, conditions grow steadily more extreme with depth. Pressure and temperature both climb dramatically the deeper you travel, and somewhere beneath the outer layers of gas, hydrogen is compressed so intensely that it begins behaving like a liquid. Then eventually, like a strange, exotic form of matter called metallic hydrogen, an electrically conductive fluid unlike anything found naturally on Earth. Scientists believe this layer of metallic hydrogen, churning deep within the planet, is responsible for generating Jupiter's extraordinarily powerful magnetic field. By far, the strongest of any planet in the solar system, nearly 20,000 times stronger than Earth's own. That powerful magnetic field creates the largest structure in the entire solar system, in a sense, larger even than the Sun itself. An enormous magnetosphere stretching millions of kilometers out into space, trapping charged particles and creating intense radiation belts around the planet, along with spectacular auroras near Jupiter's poles, similar in principle to the ones we described on Earth earlier tonight, but vastly more powerful. Jupiter's gravity, as we touched on briefly during the asteroid belt, plays an outsized role in shaping the entire solar system around it. It's sometimes described, half-jokingly, as the solar system's cosmic vacuum cleaner, its immense gravitational pull capturing or deflecting countless comets and asteroids that might otherwise wander further inward, toward the rocky planets closer to the Sun. Some scientists believe Jupiter's presence, over billions of years, has significantly reduced the number of catastrophic impacts on Earth, quietly shielding the inner solar system simply through the sheer scale of its gravity. In 1994, the world watched as fragments of a comet called Shoemaker-Levy 9 collided directly with Jupiter's atmosphere, leaving dark, bruise-like scars larger than Earth itself, a rare, dramatic reminder of exactly the kind of protective role Jupiter's gravity so often quietly plays. Jupiter also carries an enormous family of its own, more than 90 confirmed moons at last careful count, ranging from tiny captured asteroids only a few kilometers across to 4 true giants, worlds substantial enough to be considered fascinating destinations entirely in their own right, which we'll spend some time with shortly, once we've rested a while longer here around the planet itself. Jupiter even has a faint ring system of its own, far more delicate and difficult to see than Saturn's famous rings, made up mostly of fine dust rather than ice and rock, likely kicked up from small impacts on its innermost moons over countless years. There's something worth sitting with, gently, in the sheer scale of what we've just described. A planet so large that 1,300 Earths could rest inside it. A storm larger than our entire world, older than recorded human memory. A magnetic field stretching further than the Sun's own visible disk. And yet, in the grand scale of the galaxy we spent time with on another night, Jupiter itself is still, in the end, simply one planet, orbiting one ordinary star in one small, quiet corner of an unimaginably larger universe. We'll rest here a little longer, drifting closer now to the family of moons that call this giant planet home. Jupiter's great red spot, that storm we described a few moments ago, has actually been slowly shrinking over the past century or so, based on careful comparisons of historical observations. It was noticeably larger still than it is today, and scientists continue to watch it carefully, patiently, uncertain exactly how much smaller it might eventually become, or whether it might, one distant day, fade away entirely, the way smaller storms elsewhere in Jupiter's atmosphere regularly do, though on a much shorter timescale than this particular giant has so far shown any sign of following. It's worth remembering that Jupiter has been quietly watched by human eyes for just as long as Venus and Mercury, one of the 5 bright wanderers ancient astronomers tracked carefully across the sky, long before anyone understood it was a planet at all, let alone one large enough to hold 1,300 Earths. It's worth remembering gently that everything we've just described about Jupiter was entirely unknown to every human being who ever lived before the invention of the telescope. For the vast majority of human history, Jupiter was simply a bright, steady point of light in the night sky, watched and named and wondered about, but never once seen for what it truly was. An enormous world of storms and moons and magnetic fields, patiently waiting, the whole time, for someone to finally look closely enough to notice. Jupiter's family of moons is in many ways a solar system unto itself, dozens upon dozens of worlds of every size and character, orbiting one giant planet the way planets themselves orbit the Sun. Tonight, we'll rest with the 4 largest, the moons Galileo first spotted through his telescope over 400 years ago, forever changing how we understood our place in the universe. The innermost of these 4 giants is Io, and it is, without much competition, the most volcanically active body anywhere in the solar system, more active even than Earth itself. Io's surface is constantly reshaped by hundreds of active volcanoes, some flinging material hundreds of kilometers above the surface. This restless activity comes from an unusual source, not heat left over from formation, but heat generated by Jupiter's own immense gravity, constantly flexing and squeezing Io as it orbits, an effect called tidal heating, caused by the competing gravitational pulls of Jupiter and its neighboring large moons. That constant squeezing generates enormous internal friction, enough to keep Io's interior molten and its surface in a state of near-constant eruption. It's a strange, restless little world, patterned in yellows, oranges, and reds from sulfur compounds coating its surface, closer in appearance to something otherworldly than to any other moon we know of. Next outward sits Europa, smaller, smoother, and quietly one of the most compelling destinations in the entire solar system for a very particular reason. Europa's surface is a shell of ice, remarkably smooth compared to most other moons, crossed by long, dark cracks where the ice has fractured and refrozen over time. Beneath that icy shell, scientists believe there's a genuine liquid water ocean, kept warm enough to remain liquid by the same tidal heating effect that keeps Io's volcanoes active, and potentially containing more liquid water than all of Earth's oceans combined. Because liquid water is one of the key ingredients we associate with the possibility of life, Europa remains one of the most closely watched, most carefully considered destinations for future exploration. A quiet, icy world that might, just might, be hiding something remarkable beneath its frozen surface. Ganymede, the third of Jupiter's large moons, holds a particular distinction of its own. It's the largest moon in the entire solar system, larger even than the planet Mercury, though less massive due to being made up largely of ice and rock rather than dense metal. Remarkably, Ganymede is also the only moon known to generate its own magnetic field, a genuine, if modest, echo of the kind of magnetic protection we described earlier tonight around Earth itself, likely generated by a similar churning, molten layer somewhere within its interior. Like Europa, there's reasonable evidence to suggest a subsurface ocean may exist beneath Ganymede's icy crust as well, sandwiched between layers of ice deep within the moon. The outermost of the four, Callisto, is the most heavily cratered object anywhere in the solar system. Its ancient icy surface preserving a visible record of billions of years of impacts, largely undisturbed by any significant geological activity since. Unlike its three siblings, Callisto sits far enough from Jupiter that it largely escapes the intense tidal heating and radiation experienced closer in, making it, in a strange way, one of the calmer, quieter worlds in Jupiter's entire family. A patient, ancient moon that has simply weathered impact after impact for billions of years, with very little else disturbing its slow, quiet existence. Together, these four moons, Io, Europa, Ganymede, and Callisto, are sometimes called the Galilean moons, named for the astronomer who first observed them in 1610, and whose discovery quietly helped confirm that not everything in the heavens orbits the Earth. A small, patient observation that eventually helped reshape humanity's entire understanding of its place in the universe. Beyond these four giants, dozens of smaller moons orbit Jupiter as well, many of them small, irregularly shaped, likely captured asteroids drawn in by Jupiter's powerful gravity long after the planet itself had already formed. A scattered, chaotic family orbiting at all sorts of distances and angles. A quiet reminder of just how much material Jupiter's gravity has gathered to itself over billions of years. It's worth resting here for a moment, gently, before we move on. Four entirely different worlds, orbiting the very same planet, each shaped by its particular distance from Jupiter into something utterly unlike its neighbors. A volcanic world, an icy ocean, the largest moon in existence, and an ancient cratered survivor. A small, quiet reminder that even orbiting the very same point in space, worlds can turn out remarkably, wonderfully different from one another. Let's continue outward now, past Jupiter and its family, to the next giant planet, the one most people picture first when they imagine the outer solar system. Each of Jupiter's four large moons was first spotted the very same night, in January of 1610, through a telescope Galileo had built himself, small and imperfect by modern standards, and yet powerful enough to quietly reshape humanity's entire understanding of the heavens in a single evening's careful observation. There's a particular kind of wonder in picturing four such different worlds, so close together, so shaped by the very same giant planet they all orbit. Different distances from Jupiter, differences small enough to seem almost trivial on a cosmic scale, and yet enough to produce a volcanic inferno, a hidden ocean, the largest moon in existence, and an ancient, quiet, cratered survivor. Each one utterly unlike its nearest neighbor, bound together only by the same patient orbit around the same enormous world. If Jupiter is the largest planet in the solar system, Saturn is, without much argument, the most beautiful. A giant golden world encircled by one of the most striking, most immediately recognizable features anywhere in the cosmos. A wide, glittering system of rings unlike anything else we'll visit tonight. Saturn is the second largest planet in the solar system, similar in composition to Jupiter, made up almost entirely of hydrogen and helium, with no solid surface to speak of. It's also, remarkably, the least dense planet in the solar system. So much so that if you could somehow find an ocean large enough to hold it, Saturn would actually float. It's a strange thought to sit with, gently, a planet larger than Earth many times over, and yet, in a purely physical sense, lighter than water. Saturn's famous rings are made up of countless individual particles of ice and rock, ranging from tiny grains of dust to chunks larger than a house, all orbiting the planet in a wide, thin disk. Despite stretching well over 200,000 kilometers across, the rings themselves are remarkably thin. In most places, no more than about 10 meters thick, an almost impossibly delicate structure when compared to its enormous width, like a sheet of paper stretched across the length of several football fields. Scientists still debate exactly how Saturn's rings formed. One leading idea suggests they may be the remains of a shattered moon or comet, torn apart by Saturn's powerful gravity sometime in the relatively recent past, in cosmic terms at least, perhaps just a few 100 million years ago, meaning the rings themselves might be significantly younger than Saturn itself. Another idea suggests the rings have simply been there since the solar system's earliest days, leftover material that never quite gathered into a moon in the first place. Either way, the rings are dynamic and ever-changing, constantly shaped and reshaped by the gravity of Saturn's many nearby moons, some of which act as gentle shepherds, their gravity keeping the ring particles neatly confined into distinct, sharply defined bands. Saturn's atmosphere, like Jupiter's, is marked by bands and storms, though generally more muted and pale in appearance, hidden beneath a slight haze that softens its features compared to Jupiter's sharper, more vivid stripes. One particularly striking feature sits at Saturn's North Pole, a massive, persistent storm shaped remarkably like a hexagon, each side roughly the length of Earth's own diameter, a genuinely strange geometric pattern in the atmosphere that has puzzled and fascinated scientists since it was first properly observed, still not entirely understood even now. Scientists have managed to recreate a similar hexagonal pattern in laboratory experiments here on Earth using rotating fluids, offering a partial explanation rooted in fluid dynamics, though the full picture of exactly why Saturn's version has persisted so steadily for decades remains an active, ongoing area of careful study. Like Jupiter, Saturn generates its own magnetic field and experiences fast winds and rapid rotation, completing a full day in only about 10.5 hours despite its enormous size. And also like Jupiter, Saturn radiates more heat outward into space than it receives from the Sun, a quiet leftover echo of the gravitational energy released as the planet slowly continues to contract and settle, even billions of years after its initial formation. Saturn carries an enormous family of moons of its own, well over 140 confirmed at last count, more than any other planet in the solar system. We'll spend some time with two of the most remarkable of these shortly, quiet, fascinating worlds, each holding their own particular mysteries. For now, it's worth simply resting with the image of Saturn as it is, a vast golden planet encircled by a delicate, glittering halo of ice and rock, drifting slowly through the dark nearly 1 billion miles from the Sun, patient and beautiful, exactly as it has been for billions of years, largely unchanged, quietly turning, waiting for the handful of spacecraft that have ever managed to visit it up close. Anyone with even a modest telescope, pointed carefully at the right patch of sky on a clear night, can see Saturn's rings for themselves. A small, quiet thrill that has greeted curious observers ever since Galileo first noticed something strange about Saturn's shape, though it would take decades more before anyone correctly understood what those strange, handle-like protrusions actually were. Only 4 spacecraft in all of human history have ever visited Saturn up close, and only one, Cassini, ever stayed long enough to truly study it in detail, spending 13 patient years in orbit before its mission finally, deliberately ended with a final plunge into the planet's own atmosphere in 2017. A quiet, intentional ending, chosen specifically to protect Saturn's potentially life-bearing moons from any risk of contamination. A small, careful act of stewardship, extended toward a moon we've barely even had the chance to properly study yet. Among Saturn's many moons, 2 in particular deserve some time tonight. Quiet, remarkable worlds that have genuinely reshaped how scientists think about where else in the solar system life might, just possibly, be able to exist. The first, Titan, is Saturn's largest moon, and in fact, the second largest moon in the entire solar system after Ganymede. Titan holds a particular distinction. It's the only moon anywhere in the solar system with a substantial atmosphere of its own, thick, hazy, and orange-tinted, dense enough that the surface pressure on Titan is actually higher than Earth's own. Beneath that thick atmosphere, Titan's surface is genuinely strange and genuinely beautiful in its own alien way. It's the only place besides Earth known to have stable liquid on its surface: rivers, lakes, and even small seas, though not filled with water. On Titan, far from the sun, in deep and permanent cold, the liquid filling those rivers and lakes is methane and ethane, chemicals that exist as gas here on Earth, but that behave like water does here, evaporating, forming clouds, falling as rain, and collecting into lakes. An entire alien weather cycle playing out in slow motion. On a world where the temperature never rises above roughly -170 degrees Celsius. In 2005, the Huygens probe became the first, and so far only, spacecraft to land on a surface anywhere in the outer solar system, touching down gently on Titan and sending back photographs of a strange, hazy landscape, smooth stones scattered across a frozen, alien riverbed, further from the sun than any human-made object had ever landed before. Beneath Titan's icy crust, much like Europa and Ganymede before it, scientists believe there's likely a genuine subsurface ocean of liquid water, kept warm by tidal heating from Saturn's gravity. Another quiet possibility, tucked away far from the sun, that has helped fuel the broader search for life beyond Earth. The second moon worth our attention tonight, Enceladus, is far smaller than Titan, only about 500 kilometers across, and yet, in its own quiet way, just as remarkable. Enceladus has an icy surface so bright and reflective that it's one of the most reflective objects in the entire solar system, bouncing back almost all the sunlight that reaches it. What makes Enceladus genuinely extraordinary, though, are the geysers. Near its south pole, enormous plumes of water vapor and ice particles erupt continuously from cracks in the icy surface, spraying material hundreds of kilometers out into space, some of which falls back onto the moon as fresh snow, and some of which escapes entirely, actually forming one of Saturn's fainter outer rings. Those geysers are powerful evidence of a subsurface ocean beneath Enceladus's icy shell as well. And remarkably, when spacecraft have flown directly through these plumes to sample them, they've detected not just water, but organic molecules, and even hints of hydrothermal activity on the ocean floor far below. Similar, potentially, to the kind of environment here on Earth, where some scientists believe life may have first begun, near deep-sea hydrothermal vents. It's one of the most tantalizing, carefully watched possibilities anywhere in the solar system for finding some simple form of life beyond our own planet. A small icy moon, quietly spraying evidence of its hidden ocean out into space for any passing spacecraft patient enough to fly through it. Future missions are already being designed specifically to study these plumes more closely. Patient, careful spacecraft intended to fly directly through that fine icy mist and analyze exactly what it contains. One of the most promising, most anticipated searches anywhere in the solar system. There's something worth resting on gently here before we continue outward. Two small icy worlds orbiting the same golden-ringed planet, each hiding a genuine ocean beneath its frozen surface. Each holding, in their own quiet way, some of the most promising possibilities anywhere nearby for finding life beyond our own fortunate blue world. We'll leave Saturn and its moons behind now and continue drifting outward into the colder, quieter, more distant reaches of the solar system. From here, sunlight itself begins to feel almost symbolic rather than practical. Present, technically, but offering less and less actual warmth the further we travel. A quiet, gradual fading that will continue for the remainder of tonight's journey. Gently, on how differently these two small moons carry their secrets. Titan wears its strangeness openly. Thick orange clouds, visible rivers and lakes, an entire alien landscape spread out for any spacecraft willing to look. Enceladus, smaller and quieter, only reveals its hidden ocean through faint, careful evidence. A fine mist of ice crystals spraying gently out into the dark, patiently waiting for someone curious enough to notice, and curious enough to fly straight through it. Far beyond Saturn, nearly twice as distant from the Sun again, sits Uranus, a pale, quiet, blue-green planet, and in many ways, one of the strangest worlds in the entire solar system. Not because of any dramatic storm or violent feature, but because of the particular, peculiar way it simply exists in space. Uranus is an ice giant, distinct from the gas giants Jupiter and Saturn we've just visited. While still made up largely of hydrogen and helium in its outer layers, Uranus's interior contains a much larger proportion of what scientists call icy materials, water, ammonia, and methane, in various forms, compressed and heated deep beneath its atmosphere. That methane, present in small amounts high in Uranus's atmosphere, absorbs red light and reflects blue and green light back toward us, giving the planet its distinctive, pale, calm coloring. The strangest thing about Uranus, though, has nothing to do with its color and everything to do with the way it spins. Every other planet in the solar system rotates in a manner roughly aligned with its orbit, spinning like a top standing reasonably upright as it circles the Sun. Uranus, almost uniquely, spins almost completely on its side, tilted at an angle of roughly 98 degrees, meaning it essentially rolls around the Sun rather than spinning upright the way its neighbors do. Scientists believe this dramatic tilt likely resulted from an ancient, enormous collision sometime in Uranus's early history, possibly with an Earth-sized body, violent enough to knock the entire planet over onto its side. A moment of chaos, much like Earth's own moon-forming collision, whose consequences are still visible, quietly, billions of years later. Some researchers suspect the collision may have been even more complex still, perhaps two smaller impacts rather than one large one. A still unsettled question, patiently debated among scientists studying this strange sideways planet from nearly 3 billion kilometers away. This unusual tilt creates genuinely strange seasons on Uranus. Because of the angle of its spin, each pole spends around 21 years in continuous sunlight, followed by 21 years of continuous darkness, an entire human generation's worth of unbroken day, followed by an entire generation's worth of unbroken night, over and over, as Uranus makes its slow 84-year journey around the Sun. Uranus has a faint ring system of its own, first discovered in 1977, though far less prominent and far less reflective than Saturn's famous rings, made up of dark, narrow bands of material, difficult to observe clearly even with modern telescopes. The planet also carries 27 known moons, most of them named, interestingly, after characters from the works of William Shakespeare and Alexander Pope. Rather than the mythological names used almost everywhere else in the solar system, a small quirk of astronomical naming tradition. The largest of these, Titania and Oberon, are substantial icy worlds in their own right, though far less studied and far less understood than the large moons we visited around Jupiter and Saturn tonight. Largely because Uranus itself has only ever been visited up close by a single spacecraft, Voyager 2, which flew past briefly in 1986 and remains to this day our only close look at this pale, sideways, quietly strange planet. There's something fitting, in a way, about how little we still know of Uranus, tucked away nearly 3 billion kilometers from the Sun, spinning on its side, experiencing seasons unlike anywhere else nearby, patiently waiting for a return visit that so far still hasn't come. Let's continue outward now, just a little further, to the last of the true planets in our solar system. Uranus sits at the very edge of naked eye visibility, faint enough that it went unnoticed as a planet for the entirety of recorded human history before its discovery, mistaken repeatedly for a dim, unremarkable star, until careful observation in 1781 finally revealed its true, slow planetary motion across the sky. There's something quietly humbling in how little attention Uranus tends to receive compared to its more famous neighbors. No dramatic storm systems dominating headlines, no rings quite as striking as Saturn's, no moons quite as tantalizing as Europa or Enceladus. Just a pale, sideways, patient planet, tilted at an angle unlike anything else nearby, quietly completing its slow 84-year circuit around the Sun, waiting, largely unnoticed, for a second visit that so far, in all the decades since Voyager 2's brief flyby, still hasn't come. Neptune, the eighth and final planet from the Sun, sits at a genuinely staggering distance, nearly 4.5 billion kilometers away, so far that sunlight, traveling at the fastest speed anything in the universe can travel, still takes over 4 hours just to reach it. To put that in perspective, a radio signal sent from Earth, traveling at that same impossible speed, takes over 4 hours simply to reach Neptune, and another 4 hours for any reply to make its way back. A round trip of more than 8 hours simply to exchange a single message with a spacecraft that far from home. Standing on Neptune, if such a thing were possible, the Sun would appear as little more than an unusually bright star, offering barely 1,000th of the warmth and light it provides here on Earth. Neptune is Uranus's near twin in many respects, similar in size, similarly classified as an ice giant, and similarly tinted blue by methane in its upper atmosphere. But where Uranus is famously pale and calm, Neptune is a far more dynamic, far more restless world. Despite receiving so little warmth from the distant Sun, Neptune experiences the fastest winds anywhere in the entire solar system. Storms racing through its atmosphere at speeds exceeding 2,000 kilometers per hour, faster than the speed of sound here on Earth. A genuinely violent atmosphere, driven by forces scientists still don't fully understand, especially given how little energy the planet receives from the Sun to fuel such extreme activity. When Voyager 2 flew past Neptune in 1989, the only spacecraft ever to visit this distant world, it photographed a massive, dark storm system nicknamed the Great Dark Spot, roughly comparable in scale to Jupiter's own famous storm, though Neptune's storms, unlike Jupiter's long-lived Great Red Spot, appear to form and dissipate over just a few years. A far more restless, changeable atmosphere than its larger, calmer cousins closer to the Sun. Neptune's discovery itself is one of the more remarkable stories in the history of astronomy. Unlike every other planet, which were simply observed directly in the night sky over the course of human history, Neptune was discovered mathematically, before it was ever actually seen. Astronomers, studying slight irregularities in the orbit of Uranus, suspected an unseen planet's gravity must be tugging on it from further out, and using careful calculations, predicted almost exactly where such a planet should be found. In 1846, astronomers pointed a telescope to that precise predicted location, and there it was, a quiet, distant blue planet, found not by chance, but by pure mathematical reasoning, one of the great triumphs of careful, patient scientific prediction. Neptune has 14 known moons, the largest of which, Triton, is one of the more unusual worlds in the entire solar system. Triton is the only large moon in the solar system that orbits its planet backward, in the opposite direction to Neptune's own rotation. Strong evidence that Triton wasn't born alongside Neptune at all, but was instead a wandering object, likely captured from the distant icy Kuiper belt we'll be visiting shortly, caught permanently by Neptune's gravity sometime in the ancient past. Triton is also geologically active, despite the extreme cold, with evidence of geysers erupting nitrogen gas and dark, dusty material up through its icy surface. Another quiet, distant world with more activity happening beneath its frozen shell than its calm, cold appearance might suggest at first glance. There's a certain fitting stillness to ending our tour of the true planets here, at Neptune, the furthest, coldest, and in many ways loneliest of the 8 worlds we've visited tonight. A deep blue planet, howling with the fastest winds anywhere nearby, discovered not by simply looking up, but by careful, patient mathematics, quietly orbiting 4.5 billion kilometers from the warmth we all still, ultimately, depend on. Beyond Neptune, the solar system doesn't simply end. It changes character entirely, into something colder, quieter, and far less understood. It's worth sitting gently with just how young our knowledge of Neptune still is. A single brief flyby, decades ago, remains our only close look at this entire distant world, meaning almost everything we think we understand about its storms, its moons, and its strange, restless atmosphere is built from one short visit, and whatever patient guesswork has been possible ever since. There's a particular kind of elegance worth resting on in how Neptune was found, not through patient searching of the night sky the way every other planet before it had been discovered, but through pure, careful mathematics, a prediction made entirely on paper, based on nothing more than the subtle, careful observation of another planet's slightly imperfect orbit. It's one of the finest examples in the whole history of science of quiet, patient reasoning leading directly to something real, tucked away nearly 4.5 billion kilometers from the desk where the calculations were first written down. Past Neptune's orbit, the solar system stretches on much further than most people realize, into a vast, cold region called the Kuiper belt, a wide ring of icy bodies, similar in some ways to the asteroid belt we visited earlier tonight, but far larger, far colder, and far less explored. The Kuiper belt is thought to contain hundreds of thousands of icy objects, larger than 100 kilometers across, along with countless smaller fragments, all left over from the solar system's earliest, coldest days. Material that, much like the asteroid belt, never quite managed to gather itself into a full-sized planet. The most famous resident of the Kuiper belt is, of course, Pluto, discovered in 1930 and considered the 9th planet for over 70 years, before being reclassified in 2006 as a dwarf planet, following the discovery of several other similarly sized bodies nearby, which made it clear Pluto was simply one of many such icy worlds in this distant region, rather than a unique planet standing apart from its neighbors. Pluto itself is a small, icy world, roughly 2/3 the diameter of our own moon, taking 248 years to complete a single orbit around the Sun. When NASA's New Horizons spacecraft flew past Pluto in 2015, the first and only close visit ever made, it revealed a surprisingly varied and active little world, complete with towering mountains of water ice, vast plains of frozen nitrogen, and evidence of ongoing geological activity. A genuinely more complex and interesting place than many scientists had expected to find so far from the Sun. The flyby lasted only a matter of hours, New Horizons moving far too quickly to ever slow down and enter orbit, meaning humanity's one detailed look at Pluto came and went in a single brief, precious window. The spacecraft's cameras working furiously the whole time to capture as much as possible before Pluto shrank once more into the distance behind it, continuing on afterward toward the even more distant, even less understood Kuiper Belt object it would go on to visit years later. Before New Horizons arrived, some scientists had quietly expected Pluto to be little more than a dead, static ball of ice, geologically inactive and largely unremarkable beyond its distance. Instead, the spacecraft revealed a genuinely dynamic little world, one still capable, even now, of surprising the very people who had studied it most carefully from a distance for decades. Pluto has 5 known moons of its own. The largest, Charon, is so large relative to Pluto, roughly half its diameter, that the two bodies actually orbit a shared point of gravity that sits outside Pluto itself, making them in a real sense a genuine double dwarf planet system locked together tidally, always showing the same face to one another as they circle their common center. Beyond Pluto, several other dwarf planets share this distant, icy region. Eris, discovered in 2005, is similar in size to Pluto, and it was actually Eris's discovery that directly triggered the reclassification debate that eventually demoted Pluto's planetary status. Other dwarf planets, Haumea, an oddly elongated, fast-spinning world, and Makemake, another icy, distant body, round out the small handful of officially recognized dwarf planets found so far within the Kuiper Belt. Alongside Ceres, which, as we mentioned earlier tonight, holds the same modest classification despite orbiting much closer to the Sun within the asteroid belt itself. Scientists believe there may be many more dwarf planets still waiting to be discovered further out in the Kuiper Belt. Small, cold, icy worlds, so distant and so faint that even our best telescopes struggle to spot them clearly. Patiently orbiting, undiscovered, somewhere out in that vast, dark region beyond Neptune. It's worth resting for a moment on just how different this region feels from everything we've visited so far tonight. No more warm, active moons. No more colorful, swirling storms. Just small, quiet, icy worlds, drifting slowly through a deep, patient cold, so far from the Sun that its light out here is little more than a distant, dim star, offering barely any warmth at all. And yet, even the Kuiper Belt isn't quite the true edge of things. There's one region, further still, one we've barely even begun to properly explore or understand, waiting for us in the deepest, coldest dark beyond even Pluto's distant orbit. It's worth sitting with how strange Pluto's story has been, discovered, celebrated as the 9th planet for generations of schoolchildren, only to be gently reclassified decades later as our understanding of this distant region grew more complete. Nothing about Pluto itself changed in that moment. Of course, it's the very same small, icy, mountainous world it always was. Only our own understanding shifted. A quiet reminder that even settled facts sometimes simply reflect how much or how little we happen to know at the time. Far beyond the Kuiper Belt, further than any spacecraft has ever traveled, scientists believe there exists a vast, spherical shell of icy material completely surrounding the solar system, called the Oort cloud, named after the astronomer who first proposed its existence based on careful observations of comets. The scale of the Oort cloud is genuinely difficult to hold in mind, even compared to everything else we've covered tonight. While the Kuiper Belt extends out to perhaps 50 times the distance between Earth and the Sun, the Oort cloud is believed to stretch anywhere from 2,000 to as much as 100,000 times that same distance, nearly a full light-year from the Sun in some estimates, almost a quarter of the way to the very nearest star beyond our own. Nobody has ever directly observed the Oort cloud. It's simply too distant, too dark, and its individual objects too small and too faint for any telescope, even our best ones, to detect directly. Its existence is inferred, carefully and patiently through its effects, specifically through the long, looping orbits of certain comets, whose paths suggest they originate from this vast, distant shell, rather than from the comparatively nearby Kuiper Belt. Comets themselves are, in a sense, the true wanderers of the solar system, small, icy bodies, often described as dirty snowballs, mixtures of ice, dust, and rocky material. Left over from the solar system's earliest formation, tonight's story come full circle. When a comet's long looping orbit finally brings it close to the sun's heat begins to vaporize the ice on its surface, releasing gas and dust that forms a glowing halo around the comet's core, called the coma. Along with the long, glowing tail comets are so famously known for, a tail that, contrary to what many people assume, always points away from the sun, regardless of which direction the comet itself happens to be traveling, shaped entirely by the pressure of the solar wind streaming outward from our star. Some comets, called short-period comets, complete their orbits in a relatively modest number of years, and are generally believed to originate from the nearer Kuiper belt. Others, long-period comets, take thousands or even millions of years to complete a single orbit, swinging in from the far distant reaches of the Oort cloud, past every planet we've visited tonight, close to the sun for a brief, dazzling period before slowly retreating back out into that vast, cold darkness for another impossibly long stretch of time. Some long-period comets are only ever seen once in the whole of recorded human history, arriving from the deep dark, swinging past the sun exactly once, and departing again on an orbit so vast it won't return, if it ever does at all, for longer than human civilization itself has so far existed. Perhaps the most famous comet of all, Halley's Comet, returns to the inner solar system roughly every 76 years, close enough to a single human lifetime that many people are fortunate enough to witness it not once, but occasionally twice. A rare, patient visitor, tracked and recorded by human beings for well over 2,000 years, one of the longest continuously observed objects in the sky. There's something quietly moving about comets, worth resting on gently as we approach the very edges of tonight's journey. Ancient wanderers, carrying material almost unchanged since the solar system's earliest, coldest days, swinging in briefly from almost unimaginable distances, offering us, however briefly, a direct glimpse of the same raw material that built every single world we've visited tonight, before retreating once more into a darkness so vast it barely seems to belong to the same solar system at all. We're nearly at the edge now, the true boundary, where the sun's influence finally gives way entirely to the vast space between the stars. It's worth remembering that everything we've covered in this section alone, Pluto, Eris, Haumea, Makemake, and the wider Kuiper belt surrounding them, was almost entirely unknown before the final years of the 20th century. This is, in the truest sense, the newest and least explored chapter of tonight's entire journey, a frontier still being patiently mapped out, one careful discovery at a time. There's something almost impossible to hold calmly in mind about the true scale of the Oort cloud, stretching potentially a quarter of the way to the very nearest star beyond our own sun. Everything we visited tonight, every planet, every moon, every glittering ring, sits comfortably within just the innermost sliver of our solar system's true size, a small, warm, busy neighborhood, tucked deep inside an almost unimaginably larger, quieter, colder shell of ice and distance, surrounding it on every side. We've traveled a long way tonight, from the blazing heart of the sun, out past 4 small rocky worlds, through a scattered belt of ancient rubble, past 2 enormous gas giants and their remarkable families of moons, beyond 2 quieter, colder ice giants, through a wide ring of icy dwarf worlds, and now, finally, toward the very edge of everything the sun still touches. That edge has a name, the heliosphere, an enormous bubble-shaped region of space, carved out by the sun's own solar wind, the constant stream of charged particles flowing outward from our star in every direction. Within the heliosphere, the sun's influence dominates, its wind and its magnetic field shaping the space around every planet we've visited tonight. But that wind, however powerful, doesn't extend forever. Eventually, far out past even the Oort cloud's inner regions, the pressure of the sun's solar wind finally weakens enough that it can no longer push back against the thin, quiet material drifting between the stars, the interstellar medium, and the heliosphere simply comes to an end. Only two spacecraft in human history have ever traveled far enough to actually cross that boundary. Voyager 1 and Voyager 2 launched all the way back in 1977, and still, remarkably, sending back data today, nearly 50 years later, faint, patient signals traveling back to Earth from further away than any human-made object has ever traveled. Voyager 1 crossed into interstellar space in 2012, followed by Voyager 2 in 2018, each spacecraft in its own time, quietly leaving the sun's bubble of influence entirely and drifting out into the vast open space between the stars, a space no longer meaningfully part of what we'd call our solar system at all, though both spacecraft are still technically within the outer sparse reaches of the Oort cloud and will continue drifting through it for tens of thousands of years yet before they finally leave it behind entirely. Each Voyager spacecraft carries with it a small golden record, a genuine physical disk containing sounds and images of Earth, greetings in dozens of languages, music from cultures all across our planet, a quiet, deliberate message assembled by a small team of scientists decades ago, intended for absolutely no one in particular, and yet, just possibly, for whoever or whatever might one day encounter it, drifting silently through the emptiness between the stars, long after every one of us, and quite possibly our entire species, is gone. It's worth resting on that thought for a moment, gently, here at the very edge of tonight's journey. Two small spacecraft, launched by careful, patient human hands nearly 50 years ago, have now traveled further than anything else we've ever built, carrying with them a small, quiet message about who we were, drifting on, into a darkness so vast that even the sun itself, from where those spacecraft now sit, appears as little more than one more ordinary star among countless others. It's worth resting, too, on just how differently each of tonight's worlds would feel to actually stand upon, if such a thing were ever possible. The crushing, invisible weight of Venus's air, the bone-dry, whisper-thin cold of the Martian surface, the complete absence of any surface at all on Jupiter or Saturn, simply an ever-thickening fog of gas, deepening endlessly beneath you. Only here, on this one small, unremarkable, deeply fortunate planet, does the ground beneath your feet, or beneath you right now as you rest, feel like something so simple, so ordinary, and so easily taken for granted. That's the true scale of what we've covered tonight. Not just 8 planets, and their moons, and the scattered debris between them, but an entire vast bubble of space, shaped and held together by one quiet, ordinary star, stretching out far further than most people ever stop to consider, before finally, gently giving way to the deep, open dark that stretches on between every star in the galaxy. Even at the incredible distances the Voyager spacecraft have now traveled, they remain, in the grand scheme of the galaxy, barely a single step outside our own front door. The nearest star beyond our sun sits so much further away still that traveling at Voyager's current speed, it would take tens of thousands of years just to arrive. A quiet, humbling reminder of just how much emptiness truly separates even our closest stellar neighbors. There's a particular kind of calm worth resting in that emptiness, if you let it settle the right way. So much of what fills an ordinary day, back on the small, warm world we started from tonight, borrows its urgency from proximity, from how close and how immediate things feel. Out here, at the true edge of everything we've covered tonight, urgency simply doesn't apply anymore. Distance itself becomes a kind of quiet, patient stillness, nothing rushing anywhere, nothing needing to arrive on any particular schedule, simply drifting, slowly, the way everything in this story has drifted for billions of patient years already, with billions more still ahead. We've reached the edge now. Let's rest here a while before we close. It's worth sitting, one final time, with just how alone those two small spacecraft now are, further from any other human-made object than anything else in history has ever traveled, carrying their quiet golden message outward into a darkness that, for all practical purposes, has no end at all. Before we close tonight, it's worth gathering together a thread we've touched on quietly, again and again, at nearly every stop along tonight's journey. Mars and its ancient rivers, Europa and its hidden ocean, Enceladus and its icy plumes, Titan and its strange alien rain. Each of these worlds, in its own particular way, has quietly raised the same gentle question. Are we in fact alone out here, or simply the only ones we've happened to notice so far? It helps first to understand what scientists are actually looking for when they search for life elsewhere in the solar system, because it's rarely anything as dramatic as the imagery science fiction has trained most of us to expect. Nobody seriously searching Mars or Europa is expecting to find cities or civilizations, or anything resembling intelligence at all. What they're looking for is far smaller and in some ways far more profound. Any sign of the simplest possible life, microbes, single-celled organisms, the same humble kind of life that existed on Earth for well over 3 billion years before anything more complex ever emerged. Here on Earth, life has proven remarkably persistent and remarkably adaptable in ways that quietly reshape what scientists think is possible elsewhere. Organisms, called extremophiles, have been found thriving in conditions once assumed to be far too hostile for anything alive. In boiling, acidic hot springs, in the crushing darkness miles beneath the ocean's surface, near hydrothermal vents that never see a single ray of sunlight, even frozen solid within ancient ice for thousands of years, only to reawaken quietly once conditions allow. Every one of these discoveries has gently widened the range of environments scientists now consider genuinely worth searching elsewhere in the solar system for life of a similarly humble, hardy kind. Mars remains in many ways the most naturally compelling candidate, simply because of how much it resembles early Earth in its ancient past. If life ever managed to gain a foothold during that warmer, wetter period we described earlier tonight, there's a reasonable chance some trace of it might still survive, deep underground perhaps, sheltered from the harsh radiation and bitter cold of the modern Martian surface, in pockets of liquid water scientists suspect may still exist far beneath the visible ground. Rovers currently exploring Mars are specifically searching for biosignatures, chemical patterns or structures that would only make sense if some form of life, however simple, had once been present, patiently sifting through ancient rock and soil for a signal that so far has remained frustratingly out of reach. Europa and Enceladus, the two icy ocean worlds we spent time with earlier tonight, represent an entirely different kind of possibility, one that doesn't depend on sunlight at all. Deep beneath their frozen shells, in oceans kept liquid by tidal heating rather than any warmth from the distant sun, conditions may closely resemble the same hydrothermal vent environments here on Earth, where some scientists believe life may have first emerged, in total darkness, powered not by light, but by chemical energy rising up from the ocean floor itself. If life can begin that way once, in one corner of one ordinary solar system, there's no obvious reason in principle it couldn't begin the very same way twice, quietly, in the dark, beneath the ice of a small moon millions of kilometers from the nearest sunlight. Titan offers something stranger still, an entirely different kind of chemistry altogether. Its lakes and rivers of liquid methane and ethane raise a genuinely open scientific question, whether life, in some form utterly unlike anything on Earth, might be possible using different chemical foundations entirely, built around different molecules than the water and carbon-based chemistry every living thing on Earth depends on. Nobody knows yet whether such a thing is truly possible, but Titan remains one of the few places in the solar system genuinely suited to testing that question, over however many decades it eventually takes. It's worth being honest, gently, about where things currently stand. Despite decades of careful searching, no confirmed evidence of life beyond Earth has been found anywhere in the solar system. Not on Mars, not on Europa, not anywhere else we've looked closely enough to properly check. Every mission so far has really only been laying the groundwork, refining our understanding of where to look and how and for what, slowly narrowing an enormous field of possibility down toward the handful of genuinely promising destinations we've spent time with tonight. And yet, there's something quietly hopeful worth resting on, even within that ongoing uncertainty. Every single world we've just discussed remains, as far as anyone can currently say, a real, open possibility. Not confirmed, but not ruled out either. Somewhere between the dry red dust of Mars and the dark hidden oceans of two small icy moons and the strange alien lakes of Titan, an answer to one of the oldest questions anyone has ever quietly wondered while looking up at the night sky may already be waiting, patiently, for the right mission, the right instrument, the right moment to finally be found. For now, the question stays open, the same way it has for as long as anyone has thought to ask it. And there's a particular kind of peace in letting a question that large simply stay unanswered for tonight, resting alongside you, unresolved, the same way it has rested, patiently, in the minds of curious people for as long as there have been curious people at all. So that's the whole of it, or at least the shape of it. From the blazing star at the center, out through 4 small rocky worlds, each shaped so differently by nothing more than their particular distance from that same warm light. Past a scattered ring of ancient rubble that never quite became a planet, through 2 enormous giants, and the remarkable varied families of moons that call them home. An ocean hidden under ice, a moon more volcanic than any world we know, a moon with rivers and rain, just not the kind we're used to. Past 2 quieter, colder giants, one spinning almost completely on its side, the other discovered not by looking up, but by careful mathematics alone. Through a wide, patient ring of small icy worlds, and finally, out past even those, into a bubble of space so vast that only 2 human-made objects have ever reached its true edge. 8 planets, hundreds of moons, countless smaller worlds, comets and fragments, all of it held together, gently, patiently, by the same quiet gravity of one single ordinary star. And somewhere in the middle of all of it, small, warm, and impossibly fortunate, the one world where all of this happened to add up to oceans and skies and living things, and eventually, quietly, you, resting somewhere safe tonight, having just traveled, in your mind at least, further than almost any human being ever physically has. There's nothing you need to do with any of this. No part of tonight's journey requires anything of you at all, except, simply, to rest. Tomorrow, the same sun that started us on this journey will rise again, exactly as it has every day of your life, and every day for billions of years before you arrive to see it. The same moon will drift through the same familiar phases it always has. The same distant planets, if you could see them clearly enough, are still out there right now, turning slowly, exactly where we left them tonight. You don't need to hold on to any of the names, or the numbers, or the long journey we've just taken together. Just the soft, wide feeling of it all. An entire solar system, vast and varied and strange and beautiful, quietly turning around the very same sun that's kept you warm every single day of your life. Let your shoulders settle one more time. Let your breathing slow, and let the whole of it, every planet, every moon, every quiet corner of that vast, sunlit bubble we've spent tonight exploring together, simply drift gently into rest, right along with you. Good night. It's worth remembering, one final time, that everything we've covered tonight represents only what we've managed to learn so far. New moons are still being discovered around the outer planets even now, some found only in the past few years through careful, patient analysis of old telescope data. Some scientists suspect there may even be a genuine 9th planet, far larger than Pluto, drifting somewhere in the deep, unmapped dark well beyond Neptune, its presence inferred only from strange subtle patterns in the orbits of distant Kuiper Belt objects. Not yet directly observed, not yet confirmed, simply a quiet, patient possibility, waiting somewhere out there for someone someday to finally catch a glimpse of it. Wherever the true edges and true contents of our solar system finally turn out to be, one thing has remained constant throughout every single thing we've covered tonight: patience. Every world, every ring, every moon, every distant icy wanderer, all of it built slowly, over unimaginable stretches of time, by nothing more dramatic than gravity, patiently pulling small things together into larger ones. One quiet collision, one slow orbit, one gentle collapse at a time. You don't need to carry any of that forward with you either. Simply let it rest here, alongside everything else we visited tonight, as your own breathing continues to slow, and the whole of this vast, patient, quietly ordinary solar system keeps turning gently on, exactly as it always has, long after you've drifted off completely.